Alrighty. Hi, everyone. So this is the final exam review for the programming section now. So this section will cover mostly the programming aspect of it. I already gave a hint on the last slide saying that I may or may not dropped a hint on the resource tab saying what is the first programming section right here, which is totally not intentional. So it's totally made to force y'all to actually look through the resource tab and see which question it may lead to. So I'm gonna do the exact same thing here, except I actually chose a Leetcode question, specifically the rotting oranges, Leetcode 999, because I will actually prepare you a lot more compared to any other Leetcode question. So let's look at this question. I'm trying to understand it, and let's try to see how we can actually solve this just by using Zybooks and your own knowledge. So rotting orange questions. Basically, you're given an n by n grid where each value will only have three values. 0 means it's empty, 1, it's a fresh orange, and 2 means it's rotten. And every single minute, any fresh orange that is a 4 directionally adjacent to the rotten orange will become rotten. So this whole entire function basically wants to see what is the number of minutes will it take for there to be no more fresh oranges. So all of it's rotten. And if it is impossible, it's -1. So let's look at a quick example of what the problem is asking. So if we look here, we can see that the most top left orange, or let's say 00, is rotten, which is signified by an X. And the next fresh oranges that can be rotten will be on the right-hand side and at the bottom, which is what the next minute will signify, which is X on the right, X on the bottom. And now these two oranges have two neighbors that are directionally adjacent to each other. The top orange has a fresh orange on its right, and the bottom one has another one on its right as well. So those two next oranges will be rotten, which is what happens in the 2-minute mark. From there, most top right corner orange has no more neighbors. So that orange cannot spread its rotten anymore. However, the bottom orange does have a neighbor at the bottom at the bottom. So that is a 4 directionally adjacent, which means we can go top, right, down, left. So, or if you want to be more directionally, it can be north, south, east, west. So that next orange will be rotten, and only that orange will be rotten, not the neighbor, not just yet. And now the most middle bottom orange is now become rotten at minute 3, and then the right neighbor of that orange, which is still fresh, will be rotten at the 4-minute mark. So the output for this scenario will be 4, because it took 4 minutes for every single orange to be rotten, and this is our grid input. In example 2, we have a grid input, but in this case, it's -1, meaning that it can never be possible only because the orange in the bottom left corner, which is from row 2, column 0, will never be rotten. Which basically means the rotten orange will never be able to reach that fresh orange. It was never possible. And finally, for example 3, we have 2 oranges. One that does not exist and one that is rotten. And this output would be 0 because there are no fresh oranges at minute 0, so the answer is just 0. I mean, it's already been routed. So, and we have some few constraints where m is equal to length, n is equal to grid at I dot length, so it's basically our rows, and this is our columns. And we have a constraint where m will always be bigger than or equal to 1, and n will always be greater than or be less than or equal to 10. So it's not too big of a matrix. And as we said earlier, the grid value can only be 0, 1, or 2. So if you want to be fancy, you can make an enum variable here if you want to, but for my case, I will not force y'all to do anything fancy like that. So since this legal question only asked for just a function, which I have already done to prove that this example is correct, which should be submissions. You'll see us accepted 28 minutes ago, and I beat the 18%. So this actually programming section will require you to actually code a whole entire thing. So the whole entire class, if you want to say that. So since we have to create the whole entire class, which is a 2x2 matrix class with the function rotten oranges, so we have to insert and we have to create this function just to keep it simple. No deleting, nothing too fancy like that. And so you're asking, how the hell am I going to do this? So you can look back at your Zybooks. Oh, we're going to use this one a little bit more later, but you can look back at your Zybooks where let's say we have a matrix. So we have done a few matrix classes already. I think we've done it in here. No, we've done it here somewhere. Oh, let's look at matrix multiplication real quick. So we have done a matrix class already called matrix.h and matrix CPP. So where we have a vector, we have rows and columns, and we can basically take this example, but instead of calling it like a matrix class, we're going to create a graph class instead. So this question will mostly rely on graphs, if you can't tell yet. There is a tree section, but I already dropped that hint, and it's kind of an easy one to be honest, because you already done this tree inside your lab. So I'm going to do a little more difficult one, which is why I'm going to cover graphs instead. So you can look at this example where we have rows and columns. We have a vector within the vector, which is a 2D vector, and we call it vec. And for my case, we have an operator, we have a read, and we have a print. But since this problem has like a few constraints, especially where the placement of each orange is at, we're gonna have to modify this to make it work for our case. So in your actual like Zybook question, you'll be given the actual functions themselves. So you'll be asked to create an insert, to create the function you're trying to solve, and so everything. So for my case, we're gonna have to do everything from scratch, but in the actual problem, you'll be given mostly everything. So that's good. So without further ado, let's try to copy this matrix class and let's actually make it for a graph class. So since you have access to Zybooks, let's copy and paste this. And so let's go to our my VS Code. And here we have a .h file, a CPP file, and the main CPP file where you can see we have a 3x3 matrix. We want to insert these values into our graph. We have the resulting, which is the actual function, routing oranges. And we have the actual cout statement saying end line, the minutes to route oranges are blank. So, oh, wait. So yeah, so let's copy and paste this graph class, this matrix class that we done earlier inside your labs. And we're going to basically modify this to reflect our current class right now. So let's do a few changes. So the first one I want to change is this. Yeah. So since I'm using VS Studio Code, I'm gonna add a few definitions. So the nf graph underscore h, and including define. This is not required for your case, but since I'm using VS Code, I need to make this more consistent with the way I code. So it's purely just for me. And so we're going to include this vector class. We're going to change this now to our reflect the current file name, which is graph. And here we're going to keep the exact same variables. We're going to have a row, we have a column, and we have a standard input of vectors. We're going to name this graph instead of vect. So here we created our graph class already. And since we can reflect on the main CPP, we have a few things. We have the constructor, which will create our default one, which give us the size for rows and columns. And we have an insert function, which will take the position of that value and the actual value itself. And we have the routing oranges function itself as well. So we have three things: the constructor, default constructor, the insert function, and the routing oranges function. So let's just take this out, or we can actually keep this if you want. So if you don't want to delete this, you can basically change the class name to graph and change your operator. We don't need this at all. We don't need to read, just basically our insert. So we have our default constructor. We can create an overloader one, which is what we want to use. So let's create graph for int row, int column. Let me just write it down. And we have a constant standard You don't need to do this at all. If you want to include a standard library, you can do this as well. You can say using namespace standard to remove the ugly standard namespace library. You can just say vector. That will be an integer, and we're going to pass our actual graph class in graph variable by reference. As so, or we can just name this initial graph if you want to. And then from here, we can actually create the insert function. So the insert function, as I said earlier, takes 3 parameters. Insert, it will take the int row, int column, and the actual value itself, since we only have 3 options. 0 means there's nothing there. 1, it's fresh. 2, it's rotten. So we only have 3 possible values. And then here, we can actually create our rotting oranges function. So we'll need to return an integer, since we need to return the number of minutes. We'll do int oranges rotting. And then, yeah, that's pretty much it. Oh, we include a semicolon right here. And at the end, for my case, and if, since I put that at the beginning. There we go. No more errors. And this is basically your graph class right here. So we have rows, columns, the graph itself, which is a vector. We have columns. We have rows and columns, which for the upward overload, which will just take the initial graph value with the row and column, and insert, and the actual writing oranges function we want to create. So from here, we can go to our CPP file. In the exam, you may or may not be given the CPP file itself, and if you're not given that, that's completely okay. You can just write everything inside your H file if you want to. But for my case, I want to keep it a little more clean, keep it more like readable, if you want to say that. So for my case, I'll have a CPP file. So you want to include the H file you just created. So graph.h. And then from here, you want to include the Q for actually, we're going to do that later. And then from there, you want to include using namespace standard. And then, yeah, that should be good for now. So let's create our let's create our both constructors, the default and the overloaded one. So since you have an H file, you just copy and paste these function names, place them here for now. And so let's take it one by one. So this first one, we need to include the class name itself, which is graph : and then the actual function itself. And since it's been redeclared, it's because of the semicolon over here. So to not redeclare it, we're going to put curly braces instead. There we go. It's now happy again. And so here, let's use some C++ tricks you learned in 1437, hopefully. If not, I'll show you real quick. So we can actually give the row and column to the actual pair variables by doing just one simple line. You can add a colon and say row will take the current row I'm giving as a parameter, and then we can change our column, which is our pair variable, inside here, and we can let it have the parameter version of column just right here. And since it's a little bit confusing, since the computer knows which rows I'm talking about already, let's change this to R, actually just to C. So the computer knows like, hey, this is actually the private version of row, and this R is a parameter version of that. So let's change this to R and C. Let's do the same thing for the other constructor right here. Oops, my bad. It's R twice. There we go. And here, the computer actually knows for real, like this is the private variables row and column, and we're going to pass in R and C, which is a parameter version of those variables. And then from here, since we're using a vertex, we need to resize this actual vertex to reflect our new rows and columns we just gave it. So we pass in rows, pass in vector, int, and we do call columns, which is column. You go all the way until you reach 0, and then that's it. And here, you're just basically resizing your grid itself. I have a few errors, which I'm going to try to fix right now. Grid is undefined, so nothing to worry about. That's completely okay. It happens to the best of us. Ah, I called it graph instead. Yeah, there we go. Now we're talking. So I changed this to graph instead. Perfect. And this one has no plural. It's just singular. And there we go. Yeah. So whenever you have errors, it's probably just a user error like me. So yeah, just make sure you referencing your H in your CPP file. And so that's it. So for the overloaded one, we can basically do the exact same thing. Call it the class name, call in the function you want to do. And since we're not trying to redeclare it twice, we can just add curly braces for this one. Now it's happy. And let's do the exact same principle as last time, where we're going to call the prior variable and give it the actual value we want to use. So again, call row, give it the R parameter, call the prior variable column, give it the value C, which I changed initially. So I'm going to put this to R, this is C. And then finally, let's give it the actual graph. And we're going to change that to initial graph. There we go. And that's the overloaded one. Nice. And so since we're working with a matrix, let's look back at the actual CPP file that we did for the matrix multiplication lab. So here, we're using a cin variable for using standard input. And we're basically going to pass in that variable into that actual grid. But since we're not using that luxury, and since we're given like the actual the locations of the values themselves, and if we look back into main, we need to place at 0, 0 and say 2 is a rotten. So since we need to actually manually input these values into specific locations, we cannot follow our original matrix class we did. So here we're going to have to do something a little more differently now. So since we have to do go outside the usual norm, let's do this one slowly now. So it's a void function, as we did void insert, copy and paste this, pass in the class name, so it knows which one it's referencing. And so here, we actually need to check if it's within our bounds now. So most cases, or some cases, we might give like a dumb error saying, hey, let's insert a value, let's say g dot insert. That's, let's say, at the 3 by 3 location, that's going to be 0. So since this is a 3 by 3 matrix, we only have values from 0 to 2. So in some cases, I might just do an error to like, oh, let's add this at location 3, 3. But that's never possible. But that's like an insert that's within out of bounds. So we need to prevent that by actually creating a condition, checking if our actual value is within bounds. So you can say if R is less than 0, so it's a negative value, or R is bigger or equal to the number of actual row we have. So let's say I want to insert a -1, -1. That's out of bounds because it's a negative value. Or if I want to insert at position 3, 3, that's bigger and equal to the row column itself, since our initial row was a 3 by 3 matrix. So it's only possible values is 0, 1, and 2. So if it's equal to or greater than the actual rows themselves, we cannot use that at all. So let's also add the columns. So if our column is a negative value, or it's the same value or greater than the actual column variable from our class, then we need to actually throw something. So here you can do, for now, you can say return -1 to say it's impossible, since that's an actual value we can pass in. But since it's a void function, you can just say return to just skip that value itself. Or if you want to be more like a OOP programmer, you can throw an exception. So there's multiple options. You can do a return if you want to be just like one and done, since you don't have a lot of time in your exam. This also works, but let's do this more OOP style. So let's throw an error. Let's throw an out of range error this time. Nice. And let's give it a message. Let's say insert position out of graph bounds. To tell the user like, hey, this is the problem of your current input. And so this will stop the program itself. So if you're trying to run it continuously, I wouldn't recommend this, but and I would just recommend the return instead. But you can also throw. Throw will also do the exact same thing, except it will just completely terminate your program. And since I'm throwing and since I'm using an outer range error from the actual standard except class, we need to include that. So let's do include standard except. Cool. And then from here, I can definitely say this is a valid position. We can actually add to our graph. So we can say graph at row at column will equal value. So it will first check if it is within our bounds, and if it is not, it'll throw that exception. And if it is, sweet, we're going to add that value to our actual graph. So this part is completely optional since we know it's not going to happen. But if you're ever asked, you can do this check right here, saying if it's negative or if it's actually equal to or bigger than the actual prior variables, throw an exception. That's not a valid output. That's not a valid position. Else, we can just say we can actually modify the vertex itself. Cool. So now we're done with the basics, and we know this would work until we reach this right here. Since we don't, I'm not going to test the actual. We'll test at the very end with this shell script I wrote earlier, since I don't have like the luxury of Zybooks of playing and pressing the play button. So let's actually just keep going until we reach the end, which is bad practice. I would not recommend that. I would just recommend testing this function right now and commenting out this function right here. Actually, these two lines right here to check if you're actually inserting right or not. But for my case, we're going to keep it simple, and I don't have the luxury of actually debugging 3 Zybooks. So let's keep going for now, and if we need to debug, we'll do it at the very end. So now let's actually write this function, which is called orange rotting. So here, if you cannot tell, or if you are not there yet, that's completely okay. We can see we're hitting our neighbors every single time through every single minute. So at minute 0, it's the initial 0, 0 position. And then after 1 minute has passed, I always pick my neighbors, but it's always on a 4 directionally adjacent neighbors. So anything from top, right, bottom, or left, or north, south, east, west, if you be more directional. So, and after the next iteration, this 0, 0 position doesn't affect no one no more. It's completely gone. So, but the neighbors of the rotten oranges will infect the next neighbors. And this is kind of following a graph algorithm that we have done already. Let's just say a BFS algorithm. Oh, since we only have the 4 directionally adjacent oranges, we only have 4 directions we can go to. And it's always going to be those 4 directions. And we're only affecting newly rotten oranges by the new ones we have created earlier. So minute 0, it's 0, 0. Minute 1 will be 0, 1, which is this top one right here. And then 1, 0, which, well, no, 1, 1, my bad, which is this orange right here. Actually, no, it is 1, 0. My bad. 0, 1. That's what it was. And so these 2 neighbors will now be able to infect the next oranges. But we never use 0, 0 again. So it's basically getting out of the queue. So whenever we have the initial infection, we'll add that queue at minute 0. And then at minute 1, 0, 0 is out of the queue, and we'll in queue the next 2 oranges, which are the one on the right and one at the bottom. And then those oranges, let's using the right one first, will infect their right orange, which is this one right here, which is why we have an X right here. And the next orange at the bottom, actually, if more thinking about it, the right orange will infect 2 oranges at once, the one on the right and the one at the bottom, since we're constricted by the 4 directionally adjacent oranges. And so whenever we go pop from the queue, this orange right here, it has no more fresh oranges it can infect. So we're gonna also have to create or check to see that this orange has not been visited yet. So we can add a visited array as we did earlier in this lab, since we're using BFS. So we can create this variable right here, or you could be a little more lazy and do something else instead. So as we keep going through each example, we keep infecting only our neighbors, not anyone else. And so since we're only infecting our neighbors each iteration, and those neighbors will infect the next guys after once they get their chance, we're basically using a BFS tree, a breadth first search algorithm, where each iteration, we're going to check the size of the queue, increment a minute every single time we go through the queue. And from there, we're going to get the front variable, pop it, and then those will be our name. Those will be on my current orange I'm at right now. We're going to create a pair value of directions, since we're restricted to only 4, which is north, south, east, west, to be actually more consistent. So we're going to have to create some hard-coded variables that will constrict that actual direction. And we will check at all 4 directions if if not, that orange has been infected or not. So let's actually take a little break, breathe a little bit, and see how the hell we're going to do this. So let's look back at our BFS cube. So here I created a actual queue iteratively, which I do not recommend at all to do this point. I will actually recommend using the queue library this time, where basically this condition will stay the same. However, we're just going to say we're going to keep going until our queue is not empty. And once it's empty, stop, which is what this iteration is, what condition is trying to do the same thing as well. We're going to dequeue using the pop variable, which is plus plus in this iteration. We're not going to see out this time, since we're not looking for the actual path of a graph. And then this condition will stay the same. However, since we're restricted to our 4 directions, we're going to have to add a condition saying check within our ranges and has me not visited, which this part will stay the same, except we're going to be a little more lazy and check the variable is equal to 1, because 1 means it's a fresh orange. So we're only going to affect those oranges that are not 0, which is empty, or 2, which is already rotten, because if it's already rotten, there's no need to do that iteration at all. We could just skip it. And then once we infect that one, we're going to change it to true, or in our case, turn that value to the 2 variable, which means it's rotten, which means we have already been there. And we're going to enqueue it to our queue. We're going to use the push variable instead, which is why we're going to use the queue library. And let's also add a condition checking how many fresh oranges we have. And every single time we infect an orange, let's de-increment that value, because we also have the case where it's not going to be possible. And that's only the situation where it can never reach a fresh orange. So we need to make sure once all the fresh oranges are infected, which is 0, we can check if fresh is 0, give the actual minutes. But if it's not 0, give it a -1, saying that orange will never be reached. So the fresh will never be, that will basically mean all fresh oranges are not infected, because there remains 1 or more of them. So return -1. So in code itself, let's actually think about how to code this. So let's copy this variable we have done earlier, pass it in here, call in the graph class again, get semicolon out of the way because it's being declared twice. And so now let's actually code this graph. So let's first include the queue library. So I do include queue. Since we're using BFS, we need to use a queue variable. And let's actually use the actual queue class itself. So here we're going to have to create a queue via pairs. So it would be queue pair. Since it's a 2D matrix, we need to make sure we keep track of both variables. QQ, pass in Q. Basically, this will make a 2D queue instead, but we're going to use pairs instead to make sure we make it readable. But we'll keep going from here. And from here, we're going to create the fresh variable, which will keep track of all the fresh oranges we have initially. And we'll do int fresh equal to 0. And then from here, I want to check my initial rotten oranges. So the first example has 1 rotten orange at minute 0. So I basically want to look through the whole entire graph, get all the rotten oranges and add them to the queue. And if it's fresh, we're going to increment our fresh variable to make sure we know how many we have initially. So in code, we'll say for int r equal to 0, r is less than row plus r instead. Or you can do r plus plus if you want to. No, there's nothing wrong with that. For int c equal to 0, c is less than column. Oops. There we go. Plus c again. There we go. And then from here, we're going to check if the graph at that specific row at that specific column is rotten. So if that orange is rotten already, we're going to add it to a queue. Add it to our queue. So we do queue dot push to enqueue. And we'll do that row and that column. That's where we use a pair variable. Else if that graph at that row, at that column is a fresh orange, we're going to increment our fresh value to do plus fresh. You can also do the other way of doing fresh plus if you want to. Nothing wrong with that. Both ways are correct. So let's actually mix it up and do it that way instead. I think it should be correct. I haven't double checked this yet, but in theory it should be correct. So once again, this whole entire for loops will basically check which ones are rotten, and if it is rotten, we're going to push that into our queue. And if it's fresh, we're going to increment our fresh variable to make sure we know how many fresh oranges we have. Because one of the other conditions is checking if there are no fresh oranges at minute 0, just return 0. So that's our first condition. We're going to check if fresh is equal to 0. Oops. My mistake. Here we go. Okay, so if fresh is equal to 0, you can just return 0. Because there are no fresh oranges and nothing can happen at minute 0. So we just return 0. But nothing can happen. So now we're going to do our minutes now. So since we have returned 0 already, you can say int minutes is equal to -1. And we're going to create our 4 bidirectionally vector directions. We can do a vector variable. That'll be a pair int comma int. And now put, let's say, directions. Where directions will be the top, right, bottom, left. So let's work this out manually. So this is the right, I think. I'm pretty sure. Yeah. This is left. Wait, no. This is top. My bad. This is top because we're using this in the graph view. So our x variable is 0, y is 1. So y 0, 1 is the top variable. Y comma 0, x is 1, y is 0. We're basically saying we're going to the right-hand side. And then 0 comma -1 is saying 0, x is 0, y is -1. Since it's a negative value, we're going to go downwards. And let's do left-hand side, which is -1, 0, where x is -1 and y is 0. So we go to the shift to the left-hand side because it's a negative value. And that's our 4 directions right there. So now let's increment our minutes. So while the queue is not empty, so add a little exclamation point at the end, not the beginning. We're gonna get the size of the queue right now, the current size. So size is equal to queue.size. Since we're gonna have to use this in a for loop, let's just save it to a variable. And so from here, every single time we go through this BFS, which is why we're going to do the Q not empty part. Basically, we're going to copy this while loop right here. And we created our queue. Nice. Now we're inside the while loop now. We're gonna have to dequeue from the queue and not print it out. We're just gonna dequeue for now. So to dequeue from a queue, we have to make sure we are popping only for valid rows and columns. But in other words, for every single row, every single routing variable we have pushed into our current queue, we need to pop it out now. So we can increment our minutes. So every single time a BFS iteration happens, a minute has passed. And so now we have to check our queue. Since this is a pair queue, we cannot just do queue.pop directly. We actually have to go through the iteration. So for int I equal to 0, I is less than the size, plus plus I. I'm going to create an auto variable which will get the row and column separately. So auto for row, column, which will create a pair value. We're going to get the front now. So this is dequeuing from the queue. Now we're going to pop. So to remove that value already. There we go. So this is being dequeuing the value, which is front, my mistake earlier. And popping it will basically just remove that value now. So yeah, sorry for the previous statement earlier. Obviously, I used to Python where we just pop it out, which is my fault, my bad. So yeah, to dequeue, do this pair value, which because queue is in a pair form. So we cannot just pop one variable directly. We'll pop both of them at the exact same time. So when we do front, it'll get the front value as a pair, which is R comma C, and we can pop it out of our queue. And so now we need to go through every single direction possible, which is 4 times. So we need to create another for loop that will do an auto pair, and that will be for every single direction inside directions. So you can say for auto direction column, direction row, direction column, we're gonna get every single directions. So there we go. So this is just a really fancy way of doing a for loop. Haven't seen it before, it's okay. It's pretty tamed. Basically, I'm iterating through the whole entire vector of pair int. And for every single iteration, which is, let's say 0, 1, I'm going to save that to dr and dc. So this whole one pair, then the next pair, and then the next pair, until the last pair. So that's just iterating through every single pair inside that vector, nothing else. And so now we need to actually increment and modify our rows and columns based on those directions. So for every single iteration, we're going to go through directions. We're going to modify our original row in our column. So we can say int new row or nr, actually new row equal to r plus dr. And for new column will equal to c plus dr. Yeah, DC, my bad, since that's the direction column. And so here we're basically just incrementing the values to reflect the 4 possible directions. And so for one iteration, we're going to do the 0, 1. So we're going to add a 0 to row and then a 1 to column. That's for the first iteration. In the next iteration, we're going to add a 1 to the row, 0 to the column. Next one, 0 for row, -1 for column. And then finally, -1 for column, row for my bad. -1 for row, 0 for column. Wow, that's a tongue twister. And so now, once we have modified our new rows and columns, and we say that's a new row, new column, let's actually check if it's within bounds and check if that actual position is a fresh orange. If it's rotten, we need to skip it. If it doesn't exist here, we need to skip it. So this is how we're going to do our neighbors. So we're going to check if it's within our bounds, which is this check right here. Basically, instead of going through the whole entire graph as we did in the lab, we're just going to check the 4 possible directions, nothing else. And here, we're going to do the exact same out of bounds check, except to be a little more differently. So basically the one as we did for the insert function. And if it's not visited, basically it's going to be has to be false. We can do that check by being lazy and just checking if it is just fresh. If it's fresh, we can actually go there. If it's not fresh, so it's either doesn't exist or it's rotten already, just skip it. We have already been there, or it doesn't exist, so there's no need to go in there at all. So we just need to check if it's 1. So if it's fresh still, we can infect that and make that rotten now. So back to this C++, we can check the out of the within bounds check. So if new row is greater than or equal to 0, so it's not a negative value, and hold up, there you go. Same thing with the column. If it's a positive value or equal to 0, so it's not negative, and our new row does not go beyond our current bounds, so it's less than row, and our new column is also within our bounds, is not beyond the current column variable, and it has not been visited. And we can be lazy by saying graph at new row at new column is fresh. So the fresh variable is 1. And that's it. So basically, this is just checking if it's within our bounds, since we know we only can go through 0, 1, and 2. So if it's 0, it's good. If it's less than 2, we're still good. Less than 3, my mistake. And we're still good. And this is just checking if it's been visited or not. And we're going to be lazy by just saying, hey, if it's fresh, we can attack. If it's rotten, we already been there. No need to go there no more. If it's 0, it's empty. No, there's nothing we can do right there either. So if it's 1, we have not visited that orange yet. So finally, we can change that to say we have been there already by saying graph at new row and new column is equal to 2. So we have infected that one with making it rotten. Saying 2. We can push our new rotten orange into our queue now. So we need to keep infecting the rest of the oranges. So we can say push new row. Oops, not bad. Row, comma, new column. And, oh, my mistake. I forgot to make this into a pair. So make it to a pair. We use the curly braces just like that. There we go. And since we have infected a new rotten orange, we need to de-increment our fresh variable. Since that is no longer fresh, it's now become rotten. And then from there, we repeat the cycle again. We will go to the next rotten orange, get that value from the front as RNC, pop it, check every single 4 directions again, change those directions as well, check if it's within our bounds, and check if it has been visited or not, which is exactly the same principles we've done here in this BFS lab. Exact same principles. We just modified it because we don't have an adjacent matrix double pointer. We have a vector. And since we're restricted to only 4, we just modified our for loop to go the 4 routes. We modified the while loop to reflect our Q library implementation. Same with the DQ aspect and the condition right here. Same principle, check within our bounds, check if it's not been visited, and if it's not been visited or not infected, make it true, so make it infected, so make it 2 or make it true, and then add it to the queue. For the original lab, it was rear ++, and for this problem right here, it's just by push. Exact same principles. Nothing else has changed. And so finally, we're going to let BFS do its thing, and we're going to go all the way to the end of the function. And at the end of the function, we can check, hey, do we have any fresh variables left? So you can say return fresh is equal to 0. 0 means we have infected all the fresh oranges we have done initially. And so if all of them are infected, return the minute variable, which is basically return how long it took to get everyone infected. And this is done ultimately as well. Since BFS will check all neighbors within those 4 restriction directions. And we're going to increment ever since BFS is done. Else, there is a few oranges still fresh. That means it's not possible. Turn negative. And that's it. You have completely done this with me. I swear, I hope I held your hand not too hard, but also enough to not get lost. And now we can run this main CPP file by just running my shell scripts. So I'm going to clear the terminal. I'm going to just use the shell script you do for testing, except I have a build shell script. We'll basically do this. Basically, you take the main CPP file, the CPP for the graph, and basically print this out if it builds correctly, and then go to the output, else build as fill. Nothing else. It's pretty straightforward, but you don't have to worry about that. You have Zybugs. So we run this, we see that it built successfully, and the minute is 4. So to actually check the legitimacy of this graph, since I know it's correct, let's actually add this to Leetcode. So let's include this whole entire function. And since I have modified this to not include the parameter of the graph itself, actually, since it's done via class, we need to include that in the parameter section. Because if you look into the Leetcode version of it, get the code back. There we go. It's basically the same thing. It's except I just made a row and column variables, but we can just copy and paste this into our Q class and just check real quick. So let's this is the end of the function. So we're gonna copy and paste this here. Oh yeah, my bad. I'm used to pressing the fucking save button a lot. So here we have added this in a really bad way. We have we make this a little bit more nicer. There we go. So now we have added our routing oranges class, the function version into our from the class to Leetcode now. Let's run this real quick to make sure we have no errors. Hopefully we got everything correct. Oh, compile error, fuck. Oh yeah, and since this is a class version of this problem, we haven't defined our rows and columns yet. And so to do that real quick, we just look back here. So we can just say, also, this is called grid instead. So I need to change that to graph. And then just do int row equal to graph dot size to get the mn variable, and int column to get the graph at 0 position dot size to get the actually this is the this is the n variable. I think that should be correct. Let me double check real quick. I'm in doesn't this test in a while. Okay, cool. Yeah, we got all of them correct. Let's submit real quick to make sure our logic is not flawed. I hope it's not flawed. Cool. It got slower, but hey, compared to like the other solution, it still works. It's accepted. Yippee. So now we have to check that this works in Leetcode now to make sure like the logic is not flawed at all. This should not fail any test cases that you're given in Zybooks. And as you saw, we have completely done this already. So nice work, everyone. So yeah, just try to follow that logic. Like take it slow. Don't be fast about it. And just try to see if you can like get down the pattern. Like this pattern was purely BFS, nothing else. Except you just had to modify it to a 2x2 vertex matrix instead of an adjacent one. And then just from there, use the matrix class from earlier, use an exact same resize if you couldn't tell. It's the exact same one. I just didn't want to do it. I want to do it with y'all. This read is it's different now because we're not reading, we're just inserting. You have an invalid throw, which is what we got from center accept. And then yeah, so just use your resources, take your time. There's no rush, I promise. And if you can do this problem on your own and find like let's say another problem on Leetcode that where you code the whole entire thing yourself from scratch, you'll be okay. So yeah, that's all I can say. Take your time. You got this. And so yeah. Congrats. Yay. That's it. All right. Bye-bye. Good luck, everyone. You got this.